the recording. I'll stop this share and open up a new share. Okay. All right. So now you should see the problem set for the Chem 101 Unit 7 extra practice. And so what I want to do is just go through as many of these as I can as time allows. And let's see, I want to make sure I've got all the participants viewed. Okay. Yeah, and I got the chat box. Okay. So the one I want to start with is question number 6. Okay, so let's take a look. You can already see the correct answer, but let's talk about this question here. Give you a chance to read it. Okay. All right, so of course, one of the big topics from Unit 7 are intermolecular forces, what they are, their importance, how to rank them, and things like that. And so we'll start with a fairly simple one. We're looking at this structure, and we want to identify the type or types of intermolecular forces present between the molecules. Okay, so one thing we can say is that everything has London dispersion forces, right? Because anything with mass has London dispersion forces. So that's one thing I know that this molecule has, because everything has London dispersion forces, okay? Now the other types that we talked about, one of them was the dipole-dipole or dip-dip, okay? Dipole-dipole. And those are present when you have molecules that are polar or have a permanent dipole, okay? And I don't know if you remember, but I told you that when you have an organic molecule like this, a molecule with carbon and hydrogen in it, if it has an oxygen or a nitrogen with a lone pair on it, that's your indicator that it's a polar molecule. All right, and so because this one is polar, it also has the dipole-dipole. So far we've got London dispersion, we've got the dipole-dipole, but the other type of intermolecular force that's present is hydrogen bonding because of that right there. So this does have hydrogen bonds, because remember that the requirements for hydrogen bonding is that you have to have a hydrogen that is connected to either an oxygen, a nitrogen, or a fluorine, okay? And therefore it has to also be near another, lone pair on an oxygen, nitrogen, or fluorine. And if there is a sample of these molecules like in a beaker, then this molecule can feel the hydrogen bond from the hydrogen on another one of those ammonia groups. So this is, another carbon, and I won't draw the full thing, but you see what I mean? That there's a hydrogen bond because we've got that hydrogen connected to the nitrogen, and then it is close to another molecule of this compound, and there's that attractive force between that lone pair and the hydrogen on another one of these molecules. So this one has those three. Yeah, there you go. I didn't even know you could do that. That's awesome. All right, so this one, remember that in Chem 101, they don't call it London dispersion forces, they just call it dispersion. Okay, so I believe that the correct answer is E. Okay, so let's see if that's right. Oops. Well, it didn't recognize that I selected it. Let's go back. Let's go back. I want to show the question. Okay, there we go. I circled it, but I didn't select it. Okay. Yeah, okay. All right, so there's that one. And again, if anybody has any questions about any of these that I'm going through, just pipe up in the chat box there. All right, so the next one that I want to go over is, let's see, 18. So we'll scroll down to 18. Okay. Okay. So remember that intermolecular forces are related to boiling point. There's lots of physical properties that are determined by the intermolecular forces, and boiling point is one of those. And so we're asked to predict which one is going to have the lowest boiling point. And so remember that the trend is that the higher the intermolecular forces, the higher the boiling point. And so the opposite would be true. The lower the intermolecular forces, the lower the boiling point. And that's what we're looking for, is the one with the lowest boiling point. Okay, so we got to think about the intermolecular forces on these, and all of these are going to be nonpolar molecules. So this one's fairly obvious because it's just two iodines, right, connected together with a single bond. So this is nonpolar because there's no electronegativity difference, right? So this one only has the London dispersion forces. Okay. Well, what about carbon disulfide? Well, I'm going to kind of cut to the chase. You would have to draw the Lewis structure to fully figure out the intermolecular forces that are present. But when you do the Lewis structure, you get this. It looks just like carbon dioxide, except for the two types of atoms sitting out across from the carbon or connected to the carbon are sulfur instead of oxygen. Okay, so remember that these are polar bonds, right? The sulfur is more electronegative, a little bit more electronegative than the carbon, but they cancel each other out. So this is also a nonpolar molecule. All right, so it just has the London dispersion forces. Okay, and so now just comparing those two, let's just kind of pause for a minute and just compare these two. So remember that the amount of London dispersion forces depends on the mass. Okay, so iodine, if you look at your periodic table, iodine is pretty heavy. So it's 127 times 2. So this has a molar mass that's equal to 127 times 2. Okay, and the carbon disulfide, that's molar mass, its molar mass is just, well, you got 12 for the carbon, and then you've got 2 times the 32.06 for the sulfur. So it's 74 plus 12, so that's 86, which is going to be a lot less than 127 times 2. So the molar mass of carbon disulfide is lower than the molar mass of I2, iodine. And so that means that just comparing these two guys, this one, carbon disulfide, is going to have the lower amount or the smaller intermolecular forces, and therefore it's going to have the lower boiling point. Okay, well, again, I'm going to kind of spare you all of the other analysis. You can prove it to yourself later, but these guys also have a higher molar mass than carbon disulfide, higher molar mass than carbon disulfide, same thing here, and they're all nonpolar. So these are all still nonpolar, nonpolar, and that means they all just have London dispersion forces. So that none of these molecules are polar. If they were, they would have dipole-dipole intermolecular forces, and that means they would just naturally have a higher boiling point. But because if you draw out the Lewis structures, you'll see that all of the polar bonds are pointing in opposite directions and cancel each other out. Okay, remember that if you have perfect symmetry, and so like this is a perfect tetrahedron, this is a perfect octahedron. And so all of those dipoles that are in the bonds, they cancel each other out. And so you end up with nonpolar molecules. So that means that they only have London dispersion forces. And so then you're going to base the answer to this question then purely on the molar mass. Whichever one has the lowest molar mass is going to have the lowest intermolecular forces, and therefore it's going to have the lowest boiling point. And so as I said before, that's the carbon disulfide. Okay, so let me go back to the arrow. Select carbon disulfide, show the answer. We got it correct. Okay, clear the screen. All right, so that one is done. Okay, so the next one I want to do is just number 19. Okay, and again, this is the same thing, but this time we're going in the other direction where we want to know about the highest boiling point. Okay, so once again, the higher the intermolecular forces, the higher the boiling point. Okay, and think about why that is for a second. So to boil something, we have to put distance between the molecules. We have to take these liquid molecules, which are close together, and we have to give them enough energy to separate them apart from each other and become gas molecules, which have a lot more kinetic energy. Well, it's going to, if there are strong intermolecular forces keeping those molecules together, then that's going to require more energy to do. So that's why we say the stronger the intermolecular forces, the higher the boiling point. Okay, so again, just thinking about the intermolecular forces that are present, and this one is just London dispersion forces because this is a non-polar molecule. Again, it's just, two hydrogen atoms connected together, no electronegativity difference, and very small molar mass. Okay, with the ammonia, The Lewis structure for that, if you remember, is it's got a hydrogen, and then it's got a hydrogen coming out of the screen, and then we've got a hydrogen going into the screen, and then we've got that lone pair, okay? So this is a polar molecule. It's got the partial positive end where the hydrogens are, and it's got the partial negative end up here by the lone pair. So this one has London dispersion because everything does. It has dipole-dipole because it's polar, but also we've got that hydrogen bond there, right? So it also has H bonds, okay? So that's a candidate for the answer. N2, again, just two nitrogens connected together, in this case by a triple bond, but still it's non-polar, so it's just got the London dispersion forces. And the methane, we talked about that one kind of before, that's a perfect tetrahedron, right? And so it has slightly polar bonds with the hydrogens, but they would cancel each other out because they're pointing in opposite directions and canceling each other out. So this is also a non-polar molecule. So it also only has London dispersion forces. Okay, so it looks like this is the one that's going to have the highest boiling point because it has the most intermolecular forces. So I'm going to select that. Oops. I'm going to show the answer. Hopefully I got it right. I did. Okay. All right, so now I want to go to, that was number 19. So now I want to do number 21. Okay, so similar problem, but it's got a little bit different parameter. So instead of boiling point, now we're talking about the heat of vaporization. So remember what that is, the delta H of vaporization, okay? So that is a measure of the amount of energy per mole that it requires to vaporize something. So in order, the amount of energy that causes a certain substance, liquid substance, to become a gas. So it kind of gives you the same information as boiling point, but it's just a different way to look at it because you know, they don't necessarily go together. Something with a low boiling point can possibly have an uncharacteristically large delta H of vaporization, but they normally will go together. Normally boiling point and delta H of vaporization are kind of you know, two parameters that give you the same information. So we're going to use kind of the same logic. So again, the higher the intermolecular forces, then we're going to have larger delta H of vaporization. Okay. So this molecule, remember, its structure would look like this. I'm just going to draw the Lewis structure. It's methanol. Okay. So it has the carbon with the 3 hydrogens with an oxygen and then a hydrogen. And this oxygen has 2 lone pairs on it. Okay. So it's got London dispersion forces because everything does. It's going to be a polar molecule because remember I told you that any organic molecule, a molecule with carbon and hydrogen that's got an oxygen in it with lone pairs, that's going to be polar. So this also has dipole-dipole. And again, we've got the hydrogen bonding there. Okay, because you've got a hydrogen that's connected to an oxygen. And so therefore it could have that hydrogen bond with the, you know, the oxygen on another molecule of methane, or pardon me, methanol that's nearby. Okay, so that hydrogen is also attracted to that lone pair of electrons on an adjacent oxygen. So that's a hydrogen bond right there. Okay, so this is a polar molecule right here because if you were to draw the Lewis structure, you would see that it's different on one side than the other. So it's got some asymmetry, and anytime you have asymmetry in the Lewis structure, so if you were to cut it along that, you would see it looks different on this side than it does on this side. So it is polar, so it has both London dispersion forces and dipole-dipole, okay? But it does not have hydrogen bonding because in order to have hydrogen bonding, you have to have the hydrogen bound to a oxygen, nitrogen, or fluorine. The hydrogens here are bound to a carbon, okay? So automatically I know that this one's gonna have a higher heat of vaporization than this one, okay? But it will the others as well, because this one just has London dispersion and dipole-dipole. And you can kind of draw the Lewis structure and prove it to yourself later if you want. And this one right here also just has London dispersion forces and dipole-dipole because it's similar structure to this, but instead of 2 fluorines, it just has 1. but you still end up with a polar molecule. Okay, so once again, if I cut it along that bond axis right here, it looks different here than it does here. So that tells you that it's a polar molecule. So therefore you have the dipole-dipole, but you don't have the hydrogen bonding. What makes A the correct answer is the fact that you've got hydrogen bonding there as well. Okay, so I'm going to select A. Hopefully I get it right. Bada bing, bada boom. Got it. Okay. All right, so that was 21. So now I'm going to go to 24. Okay, so in this one, we got to do some ranking. So this is another kind of question that you could be asked, typical kind of question from this unit. Which one of the following correctly ranks the compounds in order of lowest enthalpy of vaporization to highest enthalpy of vaporization? Okay, so again, the idea here is that the greater the intermolecular forces, that means the greater the delta H of vaporization. So we just have to make sure, we have to find the one that correctly ranks them according to intermolecular forces. Okay, well, this one automatically I can eliminate because this has hydrogen bonding in it. The structure there is, it's got the CH3 and then an N and then hydrogen and then hydrogen. Okay, so because of that hydrogen bonding, that's going to be a very strong intermolecular force. So its delta H of vaporization is going to be very large, but it has it listed first. It has it listed as the lowest in the series. So automatically I can eliminate that one. Same thing here for the same reason. Okay, because of this hydrogen bonding, it's going to have a lot of intermolecular forces, and therefore it's going to have a large or high delta H of vaporization. Okay, well, this one looks good. It's a possibility because it puts the that molecule, it's called methylamine is the name of this. If you have to take organic chemistry, you'll learn how to name all these organic molecules. So you have that to look forward to. But for methylamine, as we just said, it is going to have a large amount of intermolecular forces because of the hydrogen bonding. And therefore, we expect that it would have the highest delta H of vaporization. Okay, so I think that this is the correct one. Yeah, because this one has it in the middle, right? And so it shouldn't be in the middle. Okay, but let's take a minute to talk about these other molecules that are in the list here. So this one right here, right? That's got the methyl group, the CH3 group, and it's got a connection to a sulfur, and which is connected to a hydrogen. So this is going to be a polar molecule, so it will have the dipole-dipole intermolecular forces, okay, because it's an organic molecule with, I said it before, is with nitrogen and oxygen, but also that's true for sulfur. It's not as polar as an organic molecule with nitrogen or oxygen in the Lewis structure, but sulfur is the same kind of situation, or even phosphorus. I guess I should say those elements from those groups. Like sulfur is right below oxygen in the periodic table, and phosphorus is right below nitrogen in the periodic table. So you look for an element that's in the group that's in the same group as oxygen. Oxygen are in the same group as oxygen. Nitrogen are in the same group as nitrogen. And if that's the case, then it's going to be a polar molecule, and so it will have the dipole-dipole intermolecular forces. Okay, and so for this one right there, that's just it is a non-polar molecule. Okay, it has this Lewis structure. This is ethane. Okay, and again, you're not expected to know how to name these in Chem 1, but there's no, there are no atoms in this structure that give it, that would make it polar. This is a non-polar molecule. Okay, so it only has London dispersion forces. All right, so this one really should be the lowest, and there it is, and then the sulfur containing one, and then the methylamine. So I think that C is the correct answer. And there it is. Okay. All right, so that was 24. So now I want to go down to 30. How are we doing on time? We're doing okay. All right, so number 30. So now we're going to move into solubility. So this is everything we've done up to this point was really lesson 1. And so now we're going to start doing a few from lesson 2, which focuses really on solubility. And so in this one, we're asked to determine which of the molecules, liquid pairs of liquids would be miscible. Okay. So I guess that implies that we need to remember what we mean by miscible. All right. And that means that, you know, they dissolve each other perfectly. They form homogeneous solutions together in any proportion. Okay. So they mix together to form a uniform mixture in any proportion. You can have a third of one and a third of the 2/3 of the other, or half of one and half of the other. It doesn't really matter, but they mix together perfectly. Okay. So the other thing that's important to answer this question is to remember that little saying, like dissolves like. Like dissolves like. Okay. And so to put that in terms of polar and nonpolar, solute and solvent, it would be like polar solutes dissolve in polar solvents, and then nonpolar, I'll just do NP for nonpolar solutes dissolve in nonpolar solvents. Okay. So like dissolves like. So what we need to think about here with these sets is this polar or nonpolar? Is this polar or nonpolar? And the same thing for each pair. Okay, so for toluene, now the structure isn't shown there. That's part of the reason why I wanted to do this one with you guys, is because it's not real clear perhaps what it looks like or what the Lewis structure is, but it's, you know what, let me erase that. Let me do this. Okay. Okay, so it's a 6-membered carbon ring. So you got 6 carbons in a ring. This is toluene. And then it's got that double bond, single bond pattern. So double bond, single bond, double bond, single bond, double bond, single bond. We talked about that with regard to resonance. But then also it has a carbon with 3 hydrogens off of one of those ring carbons. Okay, and then it also has a hydrogen off of each of these carbons in the ring. This is toluene. Okay, so all of that to show you that really what I'm talking about here is something that's nonpolar. Okay, so and then xylene, this is a straight chain. So this has got 8 carbons in it. So it's carbon, 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 carbon. 1, 2, 3, 4, 5, 6, 7, 8. And then it just has hydrogens off of these. I won't draw in all the hydrogens, but all these are just bonds to hydrogen. Okay, so again, that I can say confidently that that is nonpolar. Okay, and since both of those are nonpolar, like dissolves like, so I think that this is a situation where we have 2 substances that are miscible. Okay, now, and if you go to lesson 2, we talk a little bit about this, how water and ethanol are pretty similar because water is HOH, right? But ethanol just has the C2H5, oops, C2H5, and then an O and an H. So they're pretty similar molecules because they still have that OH, but it's just this part that's different. But they're similar enough still that they are considered miscible. I always spell miscible wrong because they're both polar. Okay, like dissolves like. So I know that 1 and 2 are miscible. I suspect that 1 and 2 are miscible. But water versus xylene, well, since water is polar and xylene is nonpolar, then I don't think that they are going to be miscible. Okay, so I think that the answer would be 1 and 2. Okay, so I'm going to select 1 and 2. I'm going to see if that's right. Okay. All right, so that was number, what was that? Number 30. Okay, so we're still doing okay on time. So I want to go down to 32. All right, so number 32. So in this one, okay, so this one asks the question, which of the following factors affect the solubility of a gas in a liquid solvent? So in lesson 2, we talk about these special sort of conditions that will allow for gases to be dissolved in a liquid, particularly water. We focus on water as the solvent. Okay. And in particular, we talk about how that as we increase the pressure of the gas, that's going to increase the solubility of the gas, right? And that's because if you have a beaker and there's water in it, let's say that this is a beaker of water, and you've got these gas molecules hovering over the surface of that water, remember that the pressure, one way to think about the pressure is that it's related to the number of collisions that the gas has with the surface. That's what really a pressure is. It's kind of a measure, an indicator of the number of collisions that are occurring with the surface of the container, or in this case, the boundary of the container would be the surface of the water. So as I increase the pressure, I'm increasing the number of collisions. And so that allows for more of those gas molecules to actually get dissolved in the water. So pressure is a factor when you're talking about the solubility of a gas in water. Okay. And then also, this is the tricky one. As we decrease the temperature, we increase the solubility. Okay. And I'm not going to try and reproduce the drawing here because of the crude tools that I have. But if you go back and look at that lesson, you'll see why. Because these gas molecules, what I want to do is I want to lower the amount of energy that they have, because if they get enough kinetic energy, they're going to escape the solution and just fly away. And so as I lower the temperature, I lower the amount of kinetic energy that these gas molecules have. And so they're less likely to have enough energy to escape the solution and to fly away. And so with temperature, it is a factor, but it's not the intuitive relationship that you might have. It's you decrease the temperature, you increase the solubility. And so another reason, it's something that you do have experience with, that may make it, that may cause it to make more sense for you, is think about like soda, like a carbonated beverage. If you want it to keep the fizz, you don't just leave it sitting out at room temperature. You put it in the refrigerator, right? And the idea there is that the cold temperatures of the refrigerator are better at keeping those gas bubbles dissolved in the beverage. So that, if that helps you remember it. But also the identity of the gas is a factor. And we don't really talk about that too much in the lesson. And that's part of the reason why I wanted to discuss this problem. And that's because if you think about it, it goes back to what we did in the previous question. It's nonpolar or polar, okay, will determine how soluble it is in water. So if we have water, then if the gas is a polar gas, which there aren't a lot of polar gases, but there are some, then the polar gas will be more soluble in water than a non-polar gas, because like dissolves like. And so if the gas happens to have a polar molecular structure, then it's going to be a factor into its solubility in a solvent like water. And so I think that the correct answer is actually D. All three of those are true. Okay, so I'm going to select D here, show my answer. Okay, that's right. All right, so that was 32. And so now I'm just going to go on to 33. That's the next one I wanted to do. Show the question. Okay, so for this one, which of the following would become more soluble in water at high pressure? Okay, so this one I'll tell you right off the bat, it's kind of a trick question because you have to think about what is affected by pressure in terms of its solubility, okay? Well, when we discussed the previous question, we talked about how if we increase the pressure of a gas, that led to more solubility, greater solubility. Okay, but you can't really increase the pressure of a liquid or of a solid. Okay, you can't really do that. There's no such thing as increasing the pressure of a liquid or a solid. So that's what I mean by it's kind of a trick question. So you can't increase the pressure of sodium hydroxide solid. You can of the nitrogen gas. You can't of this is hexane. You can't increase the pressure of a liquid, and you can't increase the pressure of a solid. So the only one that's going to become more soluble with a higher pressure is the only one that it happens to be a gas. And so that would be B. So I'm going to choose B. Okay. And yeah, that's basically what it says here. All right. So that was 33. So I want to do 34 actually too. Okay. All right. So 34 is similar. But it has to do with that temperature relationship that we talked about a couple of questions ago. So remember that for a gas, we said that if we lower the temperature, that's when we increase the solubility. Okay. And so that's what this question is asking. For which of the following would become more soluble at a lower temperature? All right. Well, once again, it's when we have a gas. Well, this is a liquid, this is a liquid, this is a solid. That's the only gas. And in general, the relationship is true for other types of substances, and that's pretty intuitive as well. For example, this C6H12O6, that's sucrose, or that's glucose. Sorry, this is a sugar, glucose, okay? Glucose. And we have experience with sugar trying to get it to dissolve in liquids like water. It's a lot more soluble in a hot liquid like hot coffee than it is in a cold liquid like iced tea. Okay, so this is the oxygen gas is the only one that is true for this statement right here. Okay. All right, so that was 34. So now I want to do 35 actually. Another ranking question. Okay, so it says, which one of the following correctly ranks the compounds in order of lowest vapor? Okay, vapor pressure. So this gets into lesson 3. That's part of the reason why I wanted to do this one, because I wanted to at least do a couple questions from lesson 3, which I don't know how many of the lessons you've got to yet, but lesson 3 introduces the idea of vapor pressure, which we've talked about before in unit 3 when we got to the principles of gases. And remember Dalton's law, where we said that the total pressure of a gas that's like hovering over the surface of a liquid would be like the pressure of, you know, some gas. We'll just call it gas I. And then if it's that gas is in a sample that includes like water, then we also have to take into account the vapor pressure. Okay, we had to subtract that out. Hopefully that's ringing some bells. And again, this is good, perhaps a review for the final. But that would be the vapor pressure of water. Okay, so that's what we're talking about here when we mean vapor pressure. So which one of the following correctly ranks vapor pressure? Well, again, this is a relationship with intermolecular forces. All of this stuff is related to intermolecular forces. And so we just got to think about what's the general principle that's involved. Okay, and again, it's this one you have to think about a little bit more. We said that as we increase the intermolecular forces, that increases the boiling point. And we also said that that increases the delta H of vaporization. Okay, but here we go. That's going to decrease the vapor pressure. I'm just going to abbreviate that as VP for vapor pressure. But it does make sense if you think about it. This means it takes more energy to separate the molecules, which means that I'm going to have to put in more energy, which is going to be evident in a higher boiling point and a higher delta H of vaporization. And so if it's harder to boil and it takes more energy to create gas molecules from liquid molecules, then I won't have as many gas molecules. And the gas molecules are what are giving us the vapor pressure. So that is going to result in a lower vapor pressure. So the overall relationship then is that the higher the intermolecular forces, the lower the vapor pressure. Okay, so if you want to kind of cut to the chase in terms of vapor pressure, the higher the intermolecular forces, the lower the vapor pressure. Okay, so think about the intermolecular forces that are involved in each one of these substances, and I'll just kind of use this first choice to list them out here. So for the ethanol, right, this has got hydrogen bonding here because it's got that oxygen hydrogen bond. And so this one has H bonding. And because it's a polar molecule, it's an organic with an oxygen in it, it does have the dipole-dipole. And because it just has mass, it has London dispersion forces. Okay, well, what about this one right here? So this one has an oxygen in it, so it has the dipole-dipole. And it has mass, so it has the London dispersion forces. But there's no oxygen hydrogen or nitrogen hydrogen or fluorine hydrogen bond, so it does not have the hydrogen bonding. Okay, and so what about this one? Well, this one only carbons and hydrogens, so it doesn't have dipole-dipole, so that means that it just has London dispersion forces. So this one has the lowest amount of London dispersion forces, so this is going to have the highest vapor pressure. This one has an intermediate amount of intermolecular forces, so it's going to have an intermediate vapor pressure, and this one has the highest amount of intermolecular forces, so it's going to have the lowest vapor pressure. Remember, the relationship is opposite. Okay, so I actually think that this one, I got lucky, I guess. This one is the correct answer because it correctly ranks them. Since this one has the lowest intermolecular forces, it's going to have the highest vapor pressure. All right, it's easier to get these molecules into the gaseous phase. So therefore, at a certain temperature, you're going to have more of these molecules in the gaseous phase, which are exerting a vapor pressure. So I think that's my answer. Let's find out if I'm right. And that's correct. Okay, I think we have time for one more. That was 35, was it? Let's go down to 39 maybe. Okay, so this is number 39. Oh yeah, so I wanted to talk about this one because for two reasons. First of all, it relates something that we talked about back in Unit 3, and that is a heating or cooling curve to the phase diagrams that we learned in Lesson 3 of Unit 7. So, you know, back in Unit 3, if you go back and look at Unit 3, you'll remember that we had this curve where we plotted the temperature versus the amount of heat that we're adding or removing. And we had something that looked like this. How if we had the solid, we would heat up the solid and eventually it would reach its melting point and start melting. And then it would heat up the liquid and then eventually we would reach the boiling point where it would start boiling and then we could heat up the gas, right? Okay, so that's what we're talking about when we, you know, what we're talking about there with the heating or cooling curve is that back from Unit 3. And so the question is, which one of these things does not show up on this kind of a curve? And what you want to do, if you haven't done Lesson 3 yet, is you want to go back and kind of look at these, you know, look for these different terms and see which ones show up on the type of curve that we learn about in Lesson 3, but they're not in this type of curve right here, okay? And what you'll see is it's the triple point, because the triple point comes from a curve, it's called a phase diagram, and that's where we plot pressures versus temperature. And so a typical phase diagram looks kind of like a capital Y. Not all of them, but they look kind of like this, where this is the solid region, this is the liquid region, and this is the gaseous region, okay? So at certain pressure, temperature conditions, you can tell if something is going to be solid, liquid, or gas. And at that point right there, they're all three present simultaneously, kind of in equilibrium. So that's the triple point. Okay. And that does not show up in your heating or cooling curve. A lot of the same information is in both of these curves. Like, for example, you know, you can tell what temperature something is going to go from the solid phase to the liquid phase, right? That would be that temperature right there. Okay, so you can get a lot of the same information from these two types of diagrams, but the triple point is not on the heating or cooling curve. Okay? So I think it's triple point. Find out if I'm right, and I am correct. Okay. All right, how are we doing on time? We're doing okay. I've only got, I think, one more left that I wanted to go over, so let's just go ahead and do it. So that was 39. So the last one I want to do is 47. Yeah, so this is one of those phase diagrams that I was telling you about. So let's answer this question. So it says, what phase change is represented by the transition from region A to region C? So we're going from region A, which is anywhere in here, to region C, which is anywhere in here. So You know, what does that mean? If I go directly from the solid phase to the gaseous phase, remember this is B is the liquid phase. And so if I go directly from solid to a gas, what do we call that? Okay, and that is something that goes way back to, I think, Unit 1. So again, another good opportunity for review here, getting ready for the final. That was called, if you remember, when we go from solid to gas, that was called sublimation. Okay, so it's kind of just a memorization thing, but also just a refresh your memory type question. All right, so let's see if I got it right. There it is. Okay. Okay, so those are all the questions that I wanted to go over. Again, I just picked out a sampling of them. I definitely encourage you do the homework, the mandatory homework assignment first, of course, but I would do as many of these practice problems as you can. And these are pretty quick ones, so you should be able to get a lot of them done. So I will just pause and see, do you guys have any questions for me? Just submit it in the chat box. Other than that, we'll call it good, but I'll wait a minute. While you're thinking about it, just another advertisement for the course evals. Make sure you do the course evals for both Chem 140 and 41. I greatly appreciate your feedback. I don't think I've had a semester of teaching yet where I haven't made some sort of adjustment to the curriculum or the way I teach something based on the feedback. I do take it very seriously, and I'm very interested in your thoughts and comments. Okay, so since I don't see any comments from anybody or questions from anybody, I will go ahead and call that good. Thank you very much. Hang in there. Have a happy Thanksgiving, and we'll just do this again next on Monday, November the 30th. Thanks.